Today, we are going to talk about the basics of a PLC, the workhorse of industrial automation. The Programmable Logic Controller, or PLC, is a special-purpose computer. It has no display, no keyboard, no printer, no hard drive, and hides in the control panel out on the factory floor. But it is still a computer. Initially, the PLC was a replacement for panels of relays, devices that turn on and off. Making a machine run using relays as logic was time-consuming and challenging, and making a change in the logic or the operation of the machine was almost as complicated as starting over. Relays also fail far more frequently than computer components, so that relay logic required more downtime to keep it running than newer PLC-based controls. On top of all of that, relays use a lot of electricity, make lots of heat and soot, and take up lots of space. An installed PLC is deceptively simple in appearance. You have a CPU module and input-output devices referred to as I/O. Sometimes the I/O is part of the CPU, and sometimes it is in other modules. The CPU communicates with the I/O, so in most systems, they share a backplane that physically holds them in place and electronically connects them. In other equipment, the I/O modules can be miles away from the CPU and connected with data cables, so that the PLC is not limited to a single cabinet or even the same building. Since the PLC is a computer, there is no need to limit it to only digital inputs and outputs. Over the years, the manufacturers added analog and other numerical inputs and outputs. To make these numerical devices useful, they included calculation capability in the programming as well, so that we can now calculate, for instance, statistical process control, or SPC values, and put PID controllers directly into the PLC program. Since this is called a programmable logic controller, we need to program it. Most PLCs are programmed using an application running on a standard desktop or laptop PLC. They communicate with the PLC using Ethernet or proprietary communication bus, depending on the manufacturer. Most manufacturers seem to have settled on Ethernet and/or USB in recent years. Unfortunately, the PLC manufacturers have failed to agree on how we program the control logic. Although most of the manufacturers claim some form of ladder logic, the specifics of that language are different for each manufacturer, including different capabilities, different ways of doing the same thing, and even differences in the order in which the CPU processes the various pieces of logic. One attempt to bring some order and interoperability to this chaos is the IEC 61131 standard from the American National Standards Institute, or ANSI. The excerpt from the ANSI webpage shown here gives a flavor of what is there. The IEC 61131 standard defines several programming languages with different strengths and weaknesses. Local programming standards, your boss or the customer, will usually specify what language you use. In this video, we are going to do a deep dive into a DCS and discuss some of the whys and hows associated with a DCS. Let's first clarify, for the purpose of this lesson, what we mean by DCS. Over the years, the term DCS has evolved from the original description, for the acronym as a distributed control system, to the use of the term decentralized control system, and they seem to be somewhat interchangeable nowadays. Regardless of which description is used, we are discussing a structure that, at the high-level view, is a system that coordinates and supervises an entire plant of many varying processes. Briefly, as a point of historical review, when PLCs were invented, they were really good at handling single processes, and were primarily used for repetitive discrete control. The advent of the DCS was for controlling many autonomous controllers that handled many continuous operations, mainly using analog control. Through time and innovation, the lines have blurred a bit between the two systems, but each in current day have some principal differences. PLCs traditionally were used for single batch or high-speed control, have a relatively simple low-cost design, and are the core of the system. Their design is flexible and generic, but completely customizable. Processing time for tasks are typically very fast. Operators usually interact and control the system using some sort of graphical display, such as SCADA. A DCS is used for continuous complex controls. They have an integrated control center much like a SCADA, which is the core of the system versus the processors in a PLC system. The DCS has a number of predefined functions that come ready to customize and deploy for various applications. Processing times are somewhat slower. Operators interact with the control system via an integrated graphical display. DCSs also have a claim that when safety is a top priority, the DCS is the most reliable system. The reason for this is because the manufacturer supplies both the control and supervisory equipment as an integrated package. The risks of integration errors are greatly reduced. There are indeed scenarios in which a PLC system would be the best option, such as smaller-sized processes, where you could employ redundant components to negate the possibility of process shutdowns. Without redundancy, you risk production halts due to the nature of a single processor controlling an entire plant. Redundancy may be deployed in either the PLC or DCS application. Just as there are circumstances for a PLC system, the use of DCS would be for larger, more complex processes that require a lot of interaction between many processors. Now that we've touched on some of the differences in the systems, let's focus on the DCS and some of its components. The DCS is a process-oriented system that uses closed-loop control. A typical plant starts with a centralized operator control center, typically called operator stations. Operator stations, in a DCS, are the heart of the system. This is where the operator can observe the operations of the plant, view process warnings and alarms, monitor production, and more. The next level of components may contain servers, archiving computers, and engineering stations. Communications with the operator station level is typically industrial Ethernet. Servers are used for the collection of data at the processor level. They are responsible for the data that moves between the operator station and the processors on the plant floor. Archiving computers are used for storing historical data that may be used for trends or compliance. Engineering stations are used for creating the projects on which the processes run. This includes hardware configurations, logic for tasks, graphical displays for operator interaction, and the administration of all those tasks through installed software packages. This is the station that is used to download the projects to the processors and the graphical displays. At the next level, you have the master controllers that supervise the individual processors as well as I/O modules. These controllers are also responsible for providing the data to the servers, which in turn supply the data for the graphical interface. Industrial Ethernet is typically used for communication with the previous level. Fiber optic may be used here when Ethernet cabling runs would be too long. At this level, the processor executes the logic and does what it needs to do in order to control the process. The next level is the field device level. Communications between this level and the processor level can be nearly any type that may be compatible with the components. Those include Industrial Ethernet, Profibus DP, EtherCAT, fiber optic, or other proprietary communication protocols. Components at this level would be devices such as transmitters, switches, valves, motors, remote or distributed I/O, etc. In short, both PLCs and DCS have their place in the market today. PLCs would work best in a small production environment, where component failure, if no redundant system is deployed, is a small risk for the application, the budget is restricted, or the tasks and I/O count are minimal. A DCS would be better used in an environment where there are large I/O counts, with many continuous processes. A processor failure in one section of the plant is not a problem for production, or risk assessment has determined that an integrated package would be the best option. The line between the two systems is nearly invisible nowadays, and it may not be long before there is no differentiation at all. Today, you will learn the difference between a SCADA system and an HMI. We will talk about the differences as well as the similarities, and also when each is used. There is usually some confusion because of the similarities. So, let's dive into SCADA for now. SCADA stands for Supervisory Control and Data Acquisition. These are used for monitoring and controlling large areas, typically a full site or plant. SCADA systems are a combination of many systems, including sensors, RTUs, or remote terminal units, and PLCs. Data from all of these systems is then sent to the central SCADA unit. That SCADA unit has its own HMI. This is why a lot of people get confused and think SCADA and HMI are one and the same. That HMI, or Human-Machine Interface Unit, on the SCADA can monitor and control anything that is connected to it. In conclusion, HMI can be part of SCADA, but SCADA cannot be part of an HMI. It's that simple. So let's talk about a common use for SCADA that I have personally encountered. While working for a water and wastewater treatment facility, I encountered a SCADA system. The HMI was located at the main water plant building. This HMI was connected to the main SCADA unit at the water plant. Each booster pump station within the water district was represented on the screen. At each location, there was a PLC that was connected to some sensors to monitor water flow, pressure, and other things, and it was able to run and control the pump itself. The remote SCADA unit was connected to the PLC system and allowed operators to control and monitor each pump station from the main plant. I'm sure you can imagine how much time and labor a good SCADA system can save a company. I like to think of a SCADA system kind of like a modern vehicle. You have several different sensors connected to different computers on board. Most of your interior features like motorized seats, climate control, and other things are controlled by a BCM, or Body Control Module. Most of your engine functions and sensors are monitored and controlled by your ECM, or Engine Control Module. These modules all send information to a main screen in your dash for you to see and control through driver controls, which is essentially your HMI. An HMI is essentially a user control station, usually in the form of a touch screen or a screen with some buttons attached. They are typically tied to a machine or process. Most HMI applications have the screen tied to a PLC that it is compatible with. Certain functions and sensors can be programmed to monitor and control on the screen itself. So what did we learn today? Hopefully, you now know the difference between a SCADA and HMI. They are different but can be used together to create a very functional and useful industrial tool. A SCADA system is comprised of remote systems all tied together at one central hub. Our example was the water treatment pumps that were located all over a water district. They were able to be controlled and monitored from a central location at the water plant. An HMI is an interface for humans to monitor and control a machine. Even our SCADA systems will typically involve an HMI. HMIs are usually connected to one machine or process, and are able to monitor and control certain functions of that machine or process.